Yeah, so today we're gonna have Yuri to present the chapter 4, I guess, which is multilingual um name entity recognition. Yuri, over to you to lead us to this discussion, and thank you for signing up to present the chapter.
Let me start sharing. Okay. Can you see my screen?
Yes, we can see your screen.
Okay. I have a presentation and I have a notebook, and I'm gonna be switching between them.
Okay,
Um,
cool.
so this was an interesting chapter. Uh, it was full of a lot of practical tips and also had some theory on how to do NAR. So those are highlights from my point of view. What was in this chapter? Uh, we'll we'll see elements of Hugging Face libraries, and like basically it builds on mostly chapter 2 and others as well. Um, it introduces an AR task, and then because we're doing it as a multilingual, we're going to discuss multilingual transformers uh, and elements that go into it, how to put model together in Hugging Face, and the results once model works and is analyzed and debugged, how to study its performance, and how to publish it and show it. So right now my model is running on Colab. Uh, like what I found is that I could not run the whole thing in Colab. Twice it failed. The notebook failed, ran out of memory at cross-lingual performance. So when we start loading uh, other other training sets, so um, I probably need to uh, kind of clear the memory, reload it, but I haven't done that yet. So I have a model like
Question: do you have the Collab Pro?
yeah, actually just
Because
bought Colab Pro again, so we can see.
yeah, because what I have found, in fact, I found the same problem when I did this next chapter generation of text, because the GPT-2 model is like 6 gig, and when it tries to run, of course, it's not this size; it's memory related, runs out of memory. But it Collab Pro asked me whether I wanted to switch to a high memory config, and it allowed me to switch to that, which made the problem go away. So you may want to try that.
Okay.
I don't know where, maybe in the runtime you'll set it up, but something to check.
Yeah, I literally just bought it, and Google showed me this make most of your collab. I guess there is more. I didn't specifically
Yeah, there
see
is a
more
more
GPU
memory
memory,
option, right? Just before where you were,
but
scrolling, and
I think it's just RAM. Mine was really GPU memory. I've noticed this before when I used Colab Pro. It actually comes with a lot more RAM, but I think in this case I ran out of GPU memory specifically. Uh, so I think I should need to kind of unload my models, or maybe like split notebook in two, because model is saved, but yeah, I haven't done this yet.
yeah, because I'm running on Collab as you are, and I didn't face a similar problem. So
Okay, and you did this chapter?
yeah,
Okay. Yeah, I
on
have.
Collabro.
I had 15 gigabytes of GPU memory, and yeah, it's not enough to go straight through. Okay, thanks. Try that. So here you can see reach the limit. So kind of a couple of interesting things that I was surprising and kind of interesting that I wanted to note before we go into like going through the chapter. I looked at NER problem before, and I was sort of predicting words or multiple words, but really on the implementation side, what you do is you only need to predict the first like entity or based on the first token, and then just spread it to the rest of the word that you are you're considering for this entity. The other thing is the code that's in the book is really clean and like really high level, really well written code for both Torch and Pandas. So I think I learned a lot by going through it. Yeah, code mostly run, which is actually like always problem with any sort of tutorial, but here it worked seamlessly. And as I mentioned, it just ran out of space at the end. I tried TPUs; they were running actually slower than GPUs. Yeah, if you're trying to do this chapter, you have to, because the model is being saved, is downloaded from the hub and being then saved. Your own model is being saved on the hub. You need to create a token. They recommend just creating a token called notebooks for all the notebooks. It doesn't need to be specialized. And one thing I kind of realized after I went through this lecture, I saw that, let me jump to the end. I have a model that we can run in the hub, but if I look at my models, I already had that model from almost a year ago. And I think this was based on the tutorial from Hugging Face. So I think there is a lecture, at least like a seminar that goes through exactly the same exactly the same material. Oh no, it's a different. Sorry, yeah, it might be a different task. Yeah, it was a different task. Never mind. Sorry. Anyway, this chapter talks about NAR, which is very common NLP task, where you have to identify entities in the text. Most common example, and entities can be anything you're interested in. It could be most common entities people use are location, people, organizations, but you can define your own entities depending on your business problem. It could be anything you're really interested in. They in transformers they continue using format for tagging other keyword. It's called input output beginning, I think. um, where you tag the beginning, the first word, and each continuous word for the entity with a different token, and then you know that it's over if you have another beginning, or you have like a zero as a non-needed, not an entity. We're going to be using this extreme data set. It's part of Hugging Face data sets, and specifically it has a name entity recognition subset called PANX. So Notebook shows you how to get, again, how to explore it in data sets. So it's a big data set, and we're specifically interested in this PON part of it that has NER in multiple languages. So they show you how to explore it, and we're specifically going to mostly work with German, which is D. Then we want to create a multilingual example, and they use Switzerland as an example of multilingual country and multilingual text. So as a data set, they create a mix of languages in some reasonable proportion to how it's used in I guess conversation written text in Switzerland. It's just I don't think it's very realistic, but you know, actually it might be. So if you have some mixture of people whose native language is German, French, Italian, so they mostly write in those languages, plus they also write in English. So what they do is they load the data set for those languages and create a mix according to this proportion. And you can see a number of training examples in the resulting data set. They explore the labels and explore the data set. The data set contains, so this is actually the one element. They look at an example of the data, tags, and where those tags are coming from. So yeah, you have we have three type of entities, and we have two labels for each, which is the beginning and continuation of the talk for the word. in the next few lines, they extract the data, and data is stored numerically, as always with neural networks. But when we read it, we want to see the readable strings. So they learn how to convert integer labels to strings for those classes, and this is how label data look. And they kind of show you how much data you can comment, how many tags they have in the data set. Any questions so far? So they want to do, apply this problem to multilingual, solve this using pre-trained multilingual transformers. And there are a lot of them. Like I think MBERT, we'll load MBERT as an example to see tokenization. We're going to be mostly working with XLM Roberta or XLM R. And at the end of the chapter, they suggest MADX as the most powerful model, at least for the time when the book was published. All those models evaluated on this core and NLL data sets, which not evaluated, sorry, initially trained on those data sets, where they have tasks of they have NER task with very similar labels, plus when they do labeling, they also have other labels, like other entities that are not those. And when performance is evaluated, it is evaluated basically going from English to other languages, evaluated on tuning on each language, and tuned on all the languages and applied to all the languages. So we're going to do the same thing. Let me switch to tokenization, and they load two models to show the difference between word piece tokenization that was used in BERT and sentence piece tokenization. So BERT uses a CLS token and separator token, which data models remove. Also, they use different tokenization to show continuation of words. So we're going to be using sentence piece tokenizer, which uses this white space special character for white space and nothing for second token or second token in the word or third token in the word. And it uses special character for the beginning and the end. They talk about pipeline in tokenization pipeline in transformers, and actually I didn't until I read this chapter, I didn't understand why it was such an interesting library, because tokenization libraries existed before that, but they have a pipeline which they represent with a picture here. which it's a non-language specific pipeline general. I think normalization just does kind of cleaning of the text. And making text more standard. Pre-tokenization does pre-split, so you can actually let your tokenizer do the split, or you can pre-split your text. Then you can actually use the specific tokenizer model, which there are a lot, and we'll be using sentence piece. Yeah, post-processing is for adding, or mostly adding special tokens. So sentence piece tokenizer works well for multilingual text because it works better for non-ASCII languages where you kind of join similar characters, which I'm guessing example would be like a different European languages where you have variations of O and which really people use both. So you really want multiple, like in most of the cases, you really don't care about multiple spellings. Yeah, so by default, it tries to work for all the languages that are written in Unicode, but sometimes you want to write tokenizer specific for specific languages. Also, it allows you to go back and forth. It allows you to restore original text from tokenized version, which is convenient. All right. Any questions on tokenizer? Okay. So next they introduced the NER as a transformer task. So in chapter 2, we created a classification task for the string, the sentiment analysis, which basically took the whole sentence and produced one answer out of all the hidden state. So label was applied to the whole to all hidden state at once. There's only one label. So here we have task of token classification, where all the tokens, or most of the tokens, so some of the tokens will get classified, yeah, so it's a different setup. But again, the base of transformers look exactly the same. So the interesting kind of approach that one of transformer class in Hugging Face is that it is built for reuse, it is built for transfer learning. So you can do it with any other model, right? Of course, you can remove. You can take like any other model, remove the top layer, and then add your own. But Transformers class in Hugging Face is doing it explicitly. So every model they build has the original pre-trained model, and then model with the head for specific task, and they use convention for model naming. So it's an original model for specific task, so specific head that you're going to be adding. So in this case, yes, it's model for specific task. So in this case, model was XLM Roberta for token classification task. Because you want configuration, model configuration that will produce classification for each or for multiple tokens. Most of the time, for most common tasks, those models already exist. So as an example, we're going to go through how to create your custom models. But I think for most of the pre-trained tasks, somebody, either the author or somebody else already created like popular heads for the model. But if you have if you want to build the custom model, you need to perform two operations. You want to create a model, and you want to tell, and you want to specify how to load it. So this is an example that they're showing here. We create a new class, which we extend existing class, and we override two methods, init and forward. So you can see in the init, we create the underlying model. We add the head with dropout and linear layer, and then we add weight initialization.
Yuri, I have a question here.
Yep.
One of the things that confused me here was, according to the diagram, we are not classifying a single token, right? Like the CLS token, we are classifying all the tokens. So if you look at the picture here, the linear layer should have the length of tokens times the hidden size as the input, and the output will again be, you know, the number of tokens, and then the same thing, right? Because per token you're going to get a label. But if you see the construction of the model, they give it, the classifier only gets the config.hidden size as the input. So that was something that is config.hidden size the size of the all of the tokens? Because I thought the hidden size is just the hidden size of the edge, the single token's hidden size. So I didn't print out and check that, but that connection or that thing confused me, because shouldn't it be that it should follow the picture, therefore the connection should be for all the hidden sizes, or the totality of the hidden sizes?
Yeah, and my notebook just got disconnected, so we can restart it if we want to explore it. We should do that. but so I see that we pass in hidden size. I think that's coming from output of the Roberta model. It's the same config. When we create this class, I guess I can look at where we create this class, and then number of labels I think is 7, right? So we have 3. Yeah, we have 3 location, person, and organization, beginning and continuation, and not an entity. Let me see where we create this class. Instantiate this class. Yeah, so when we create config, it's number of labels is number of classes in the tags, so 7.
Yeah, that's for each token gets resolved into one of the 7 classes. That's
yeah.
But the input is the thing that confuses me. I guess we'll have to look at what
picture.
config.hidden size is for the model and whether that is the sequence times the edge.
Yeah,
Because
yeah, maybe it's
here,
a bad. Yeah, maybe it's a bad picture because you get it for every, like basically you get that output for every token.
right. But then the input should also be, the input to the linear should be the sequence length times the size of each token, right?
So I explored it. The linear layer is like shared weights. So it's like if it's using the same weights for every token, basically. And that's why it's the hidden size is the embedding and is the hidden size of the token. Of each token.
So so the linear layer is not as shown in the picture. So it's one single quote unquote single linear layer which shares all the weights for each of the tokens. It's just that it's applied to each of the tokens with the same weights.
Yes.
That's why it is the way it is. It's just one hidden size to config.num labels. Okay, I didn't get that. Okay, that helps. So it's not, the picture is kind of misleading then.
Yeah, it's
because
kind of
the picture in a linear layer, it should be n times the hidden size to n times the number of labels, right? If the picture is accurate. But what you're saying is the linear layer is shared weight linear layer with each of the hidden sizes just going through a same linear layer in a sense.
Yeah.
Because the weights are shared across all of the hidden size inputs.
Yes, that's what it looked like from when I was figuring out the sizes and stuff.
Okay, that makes sense. Okay, thanks. That helps a lot. The second question I had similarly is, it also, it grabs output 0. And I was wondering what the purpose of that indexing into the output is rather than just the outputs. Anybody know the configuration of the outputs and the reason it kind of indexes into it? And the reason I ask is, if we are creating these things ourselves, then, we need to understand why outputs right there won't work, and we need to index in if you're building it. And I just want to get that in my head of why it's necessary to index into the outputs rather than just.
Oh, you mean this one?
Yeah.
Yeah, I didn't. I noticed it. I didn't explore. Again, I didn't explore it. I
probably should print out what the outputs look like and why the indexing into outputs is necessary.
Yeah, maybe there's just more than just outputs that's being returned from the model. So the actual hidden state is in the just the first. So,
anyway, we can proceed, but I was just, those were my confusion. The first one, thanks, Riley, for clearing that up, and I'll play with outputs, print it out, and look at what it prints out and why. I was going to check the typical output from a Roberta model in order to understand it, but that I'm sure it will be there in the Hugging Face documentation.
I looked up the documentation. It returns a kind of like a tuple from the output, and the first entry of the tuple is last hidden state, and then there's pooler output, hidden states, passkey values, attentions, and cross attentions.
Okay, so really hidden state is in the first.
So hidden state is in the first index?
Yes.
Or the index?
I think when you instantiate your model or somewhere, you can configure what's going to output, right, Srinivas? So sometimes you might see different things will be available based on how you configure your model configs.
Yeah. But okay, I think from what Riley said, it looks like output 0 is what you want, and you have to index into it in order to get that. Okay.
Okay, so we apply a linear layer to in the forward method. We apply this linear layer to the first dropout, then linear layer, and then we calculate cross entropy loss. And I guess the output is the same. It's whatever all the models and transformers expect. And then we need to configure when we instantiate, we load this custom model, we need to configure it. And sorry, I have like a physical book, so I'm cheating and looking at the book because it was it's difficult to remember all this. So they use autoconfig that allows you to load pre-trained models and create this configuration. And then they add prediction on top of it, which is I guess takes the maximum of the prediction from the linear layer. Okay. Let me restart it because I really want to have a model. So we defined the model that classifies tokens. Now we want to make it specific to NAR. And in order to add labels into the data set, you want to create a function that creates those labels, and then you pass this function in the map function to the whole data set. So yeah, so as you're doing it, so you really only care about the first subword, and the rest of them shouldn't be labeled. So yeah, so you want to create this function that will recognize and align labels and apply it to the data set. And what they do is if it's a first subword, they take a label. Which is label ID is this. And if it's not the first subword, they label it with -100 because PyTorch will ignore the cross entropy will ignore input from the label was -100. So if those were, this is an example of the phrase that was tokenized. So you have, and they have a convenient mechanism, which is which they mention is that the tokenized input actually knows the original words. So you can see that the labeled original words are marked here, was enumerated here. So then labeled are applied. Those are numeric labels, and those are string labels. So what happens here, and this is I think I understand this, but let me try to postulate something. So we're not going to have any labels on second and third parts of the word. So really, weights on them shouldn't matter, or weights that are coming from those, like signals that are coming from those tokens. But because of attention, the first part of the word, the first token of the word, still lives within the sentence. So it's actually very much like its hidden state is very much influenced by his second word, third word, subword, as well as like everything else in the sentence. So I think that's how it works. But we just don't label only kept on the first subword. Okay, so after this function is created, you apply it to the data set, and it can be used. Any questions here? So they show how to create performance metrics, which now I saw where cross entropy is created. So yeah, they use this SQL sequences evaluation library to do comparison, and this library takes sequence of sequences, and then it does comparison. So in order to use this library, the predicted labels and actual labels are reshaped in the same way. So you create lists of lists and add labels, actual ground truth labels and predicted labels. Then they describe how to do training. They introduce training argument class. where you specify a lot of information for training. Now, in order to create, okay, so I restarted, but my my token was saved. I think in order to download the model, I needed to be registered, so I provided my token here. So using sequence evaluation metric, one computes F1 score. That will be produced as model runs. Then one creates a trainer and starts training. And it's running pretty fast. Okay. I think next chapter is really interesting. They basically show you how to debug the results, and they do it through error analysis. And I think that and they suggest, first of all, first of all, they want to do it on non-specific examples. So they create this extra method that will provide, that will give you all the losses for all the. It kind of gives you the full output. And they apply to validation set, and then they get answered in this in the following manner. So it's for each sequence, for each sentence, they show you actual labels, losses, numeric losses, predicted labels, and the actual input tokens corresponding to those input IDs. Then they use this a really interesting function on Pandas series called explode that basically changes because those are all sequences of the same length. They actually put them into the data frame. So it's the same information, but vertically in the data frame. And then they calculate on the whole addition set. They calculate loss. They actually they do it for loss, and they do it later on. They do it for other parameters. Sorry, so they do it for loss, but they look at loss for different input tokens and for loss at on different labels, and they show you count, mean, and sum, and they have interesting way of analyzing this data. So if we look at the first one, zeroth input token is a white space, and they interpret it right. You have a lot of them. Its losses, mean loss is really small. Overall loss is big just because you see it a lot, but the mean loss is very small. Yeah. But then and then you can analyze what was average loss on each of the input IDs, which is basically each token, and translate it into tokens. And they do the same thing with labels. So you can see what was the count, mean, and sum loss for each label. And of course, more traditional way of looking at it is confusion matrix, which they pull from sklearn. And you see that it's classified, it works fairly well, except for organization. Quite often the first token organization is classified as a second or non-first token of non-first part of the organization. The word, sorry, not the token. And then the other thing they proposed is so you kind of do this because you want to know how your model perform. You want to like see that it's actually like doing something reasonable. And then they when you look at the results, they suggest that you look at results with high losses, which is kind of a normal procedure. You want to see like your worst errors and see where they're coming from. This also kind of allows you, what they're saying is that you can also analyze peculiarities of your data set when you're doing that, because United Nations was predicted to be a person, same as Central African Republic. So that was like a high loss. Anyway, any questions here? So now that the model is trained, they actually start applying it, and as with any other multilingual tasks, and sort of you look at how well transfer works, how well you can do zero shot going from one language to another, and when you should be doing zero shot, and then what can you get from training on multiple languages. So we chose to use F1 score, which we implemented before. Actually, it's right there in the metric. Okay, so it's in the you can get it directly from the metric. And then they show performance. Basically, they create a French data set and apply a German model on French data set and apply it to Italian and English models, and you get worse performance as expected. Then they question, like, when should you do zero shot transfer, go to a different language, and then so they take they train language, they train a model on the language where they want to evaluate. So they train it on French and apply it to French NER. And this is a training on a very small data set. F1 score is terrible. And then they take different sizes of the training set, and you get better and better performance. So you can show where basically if you had I think less than 700 samples, zero shot gives you better answer. But of course you can do both. You can do zero shot, and they didn't try that. Like in theory, one can do take a model that was trained on. You can take a model that was trained on German language and then fine-tune it on those 700 samples. That should give you better performance. I was actually thinking of trying to do that because they haven't done that. What they did instead is they just trained on all the languages at once. They created a database of all the languages that we were looking at in the beginning, and then the training on it. And I'm running it, but this model should run out of memory as well. But they get pretty high accuracies. So their conclusion was like multilingual training works well. And the interesting thing is, if you train on like 3 languages, it gives you higher performance on the 4th language, and that's I think people saw that result before. The other interesting thing that in this notebook is interaction with the model, which I already trained my model. So I have it on. It's been published on my account, so I can now interact with it through the web. It's slow the first time when model is loading, and it's pretty fast after that. in here they only show. Yeah. So let's try. Well, the thing that they didn't show in this lecture, but one can do more interesting interaction with the model using not just hosting it through this simple web interface, but you can actually build a little bit of a web interface and host some interaction on Hugging Face spaces. So you can use a different framework to actually make model a lot more interactive. All right. Any questions? So I don't know. To conclude, this was kind of a second task showing how to build models on top of transformers. This time it was a token classification task applied to NER, and it had a lot of interesting code and kind of things to look at. One thing I wanted to try after this, I wanted to try to do this MADX that they recommend, but also I actually want to explore the model a little bit, and yeah, we'll try to either unload some of the models just so I use less memory, or try to increase GPU memory. Any questions? Can you guys still hear me?
Yes, we can hear you.
Hey, has anybody here done entity classification on something other than the normal? You like trained your own model for products or something that's not a normal that you don't always see, or just customize their own model.
So we're doing it right now, but yeah, I can't show it yet, but maybe in a couple of weeks I can show something.
Remind me what the basic technology you're using for that strategy.
So we have our own entities, and we use various ways of. So the most difficult part is labeling our entities. Right after we label it, the model is standard. So we use different kind of labeling techniques. We tried doing it manually. We tried doing it sort of programmatically. Now we started using Prodigy, and I think we're using Label Set right now, which is like a clone of the free version, like website that's very close in functionality to Prodigy.
So you're not using transformers, are you?
No, we're using the Hugging Face models.
Okay. Okay. So you're doing token classification.
Yeah.
Nice. I mean, I kind of knew all that already, but it's interesting to hear. And what are your entity types? I know products, but do you have specific types?
Yeah, it's sort of we call them items and metrics, but they're like sort of, you can think of them as nouns and verbs of products. And location.
Give us a verb. Give us a verb.
A verb would be inflation.
I get it. So corn is the noun, or grain.
Yeah.
How about that? Wheat.
Yeah.
Wheat is the noun, and inflation is the verb.
Yeah.
Interesting.
Oh,
yeah, because you don't think of any tagging as like.
Yeah. Product.
You know, usually you think of nouns. Yeah.
Yeah.
Cool.
Hey, Yuri, I had a query here with respect to data correlator. Why is it being used here, or is there any difference if we use data correlator versus not using it in this trainer?
Oh, to fill the sentences to the maximum length.
Mm-hmm.
I think that's what it. I don't know if it will
the
work.
data collator, Mayank, is used when you want to pad to the length, to the max length in the batch versus padding it to the max length of the model.
Mm-hmm. Okay.
So it helps you keep the lengths relatively small, meaning if you were to pad to max length for every batch, when the batch doesn't have more than X, then you're lengthening the sequences unnecessarily. The data collator helps you avoid that. It just pads to the max length in the batch.
So it's for batch. Okay. Ooh,
Yeah.
That's also why we talked about last time sorting your sequence lengths by sequence length, and then when it batches, I guess the collator will also. Oh, I don't know.
I don't know if they sort. Like I've seen. I think in from what I remember in FastAI, they were sorting sort of. They had this like a not exact sort, but sort of. I think they called it sortish, so they were somewhat similar. So central. They put sentences with somewhat similar length in the same batch. I don't know if anything like that is done here.
Does the shuffling of the training data also makes a difference here? If we shuffle it based on if we are trying to, I don't know, get a kind of a performance, or if we are trying to increase our score. So does the shuffling here also helps?
From what I can see in the notebooks, they shuffle when they do the, if you can, I'm staring at the piece of code where they actually shuffle when they concatenate the splits.
Okay.
I don't know whether I believe they've done it elsewhere too, if I recall, but I could be wrong. I'm talking from memory. Yeah, right there where Yuri has it, fine tuning on multiple languages, you see them shuffle.
if they use shuffle anywhere else. Yeah, I think they shuffle everywhere.
Yep.
Okay. All right. Any other questions?
No, thank you.
Okay, thank you.
Yeah, I think we have the next chapter, chapter 5, text generation, and we don't have a presenter. I just put my name. Maybe I will be able to volunteer to present chapter 5. But still, we have chapter 6 and 7, summarization answering in a couple of weeks. So please, if anyone is willing, you can sign up. Okay, thank you very much. And yeah, see you next.
Thank you.
Thanks, Yuri.
Agree.
See you.
Thank you.